unless otherwise specified, we will take as the domain of a function the set of all real numbers for which the function makes sense. For example, let's look at two functions. F of x equals 1 over x, and g of x equals the positive square root of x. Here we have two functions. Now, when I say the domain of the function is the set of all real numbers for which this function makes sense, the two things that I'm most concerned about are division by 0 and square roots of negative numbers. I cannot divide by 0, and I cannot take the square root of a negative number in the real number system. Let's see, for example, if I said if x is equal to 3, you could substitute x equal to 3 into this function. F of 3 would be equal to 1/3. F of 7 would be equal to 1/7. We could not, however, substitute in 0 because f of 0 would be 1 over 0, and we cannot divide by 0 in our mathematics. So we will take as the domain of this function, f, the set of all numbers x such that x is not equal to 0. Alternately, we could write this in interval notation as minus infinity, comma, 0 in parentheses, union 0, comma, plus infinity, meaning everything on the real line from minus infinity to plus infinity excluding the number 0. The parentheses indicate that 0 is not included. All x but not 0. Now similarly, let's look at this function g and figure out what values could be substituted in for x. Here we could substitute, for example, x equals 4. The square root of 4 is 2. We could substitute x equal to 2. The square root of 2 is a real number. We could substitute in 0. The square root of 0 is 0. No problem. However, we could not substitute in any negative numbers. If we tried to substitute the square root of, for example, minus 1, that would not be a real number. So the domain of g would be the set of all x for which x is greater than or equal to 0. We can only substitute in values that are not negative numbers. Okay, so set of all x for which x is greater than or equal to 0, or in interval notation, we would write 0 to plus infinity, but a bracket here to indicate 0 is included. This would be all x values greater than or equal to 0. In fact, we could think of this as all x values less than 0 or greater than 0, but not equal to 0. Okay, because this is a parentheses, 0 is not included. So this means x greater than 0. This is x less than 0. So x can be less than 0 or greater than 0, but not equal to 0. Here, however, we want only those values which x is greater than or equal to 0. Now, I just want to spend a moment discussing why I have mentioned that we cannot divide by 0 or take the square root of a negative number in our mathematics. When we have a division problem, for example, 12 divided by 3, if we say 12 divided by 3 is 4, this means we have 12 items, and we divide them up into 3 groups. Each one would contain 4 items. In other words, division is defined in terms of multiplication. 12 divided by 3 is equal to 4, since 3 times 4 is equal to 12. And we can multiply both sides of this equation by 3 or cross multiply to see that 12 is equal to 3 times 4. Similarly, if we have 0 divided by 7, the answer would be 0, because when we cross multiply, 7 times 0 equals 0. The problem that we get comes into play only when we try to divide by 0. If, for example, I have 8 divided by 0, and I want to know what that answer is, well, whatever answer it is, 0 times that number should be 8. But there is no real number, such that when you multiply by 0, you're going to get 8. That means that 8 divided by 0 is not a real number, 8 divided by 0 is not defined. Okay, so this is not defined. Because if it was defined, 0 times that number would be 8, and we don't have an answer like that. So since this cannot occur, 8 divided by 0 is not defined. Similarly, we can never divide by 0. Now, when it came to square roots, I was concerned about the square root of a negative number. If I say that, what is the positive square root of 4? Positive square root of 4 is 2, since 2 times 2 is equal to 4. What about the square root of minus 4? What about the square root of a negative number? Let's say we're looking for the answer for the square root of negative 4. Well, I want a number which, when multiplied by itself, will give me minus 4. Well, it can't be a positive number because a positive times a positive would be positive. It can't be a negative number because a negative times a negative would also be positive. And 0 times 0 is equal to 0. So there's not going to be any real number that is the answer to the square root of minus 4. Okay, so since we do not have a real number that does that, this is not a real number. So the two things we were most watching out for: division by 0, which is not defined, the square root of a negative number, which is not a real number. Now, I want to mention that it would be all right to have, say, the cube root of a negative number. The cube root of, for example, minus 8 is minus 2, since minus 2 times minus 2 times minus 2 is equal to minus 8. If you take minus 2 3 times, it's a factor, you do get minus 8. So it's not the cube root of minus 8 that I'm having trouble with. It's square root of a negative number. Actually, it's any even root of a negative number. Odd roots of negative numbers are okay. An odd root of a negative number is all right. An even root of a negative number would mean that I wanted to take the number an even number of times and have it come out to be negative. And we can't do that in the real number system. Okay, so when we're working out domains of various functions, remember that it's going to be the set of all values for which the function makes sense. We're going to throw out anything that would give us division by 0, or the square root, or actually any even root. For example, the 4th root or the 8th root, any even root of a negative number will also be thrown out. Okay? But cube roots, odd roots of negative numbers will be perfectly okay. Okay, let's start with the function f of x equals x squared plus 5 for x between 0 and 6. If you remember, when I started the tape, I said that we'll take as a domain of the function, unless it's otherwise specified, we'll take as a domain the set of all numbers for which the function makes sense. Okay, but if it is otherwise specified, for example, he tells us here that x is only to be between 0 and 6, and that takes precedence, and the domain of the function in this case is simply those numbers between 0 and 6, which we can write in interval notation like that, or the set of all x values such that x is between 0 and 6, including the endpoints. Okay, so if a domain is explicitly stated, we write that down. On the other hand, if we had another polynomial, for example, g of x is x squared plus 3x plus 2, and there was no domain specified, then here, for the domain, I would write minus infinity to plus infinity, or all real numbers, because I do not have any fraction where I have to worry about division by 0, and I do not have any square root or any even root where I'd have to worry about the square root of, say, a negative number. So basically, there is nothing to cause any problems here. This function makes sense for all real numbers, from minus infinity to plus infinity. If you want to plug in 7, you would get 7 squared plus 3 times 7 plus 2. If you wanted to plug in minus 5, you get minus 5 squared plus 3 times minus 5 plus 2. Every real number could be substituted in for x. Okay, let's try. For our next example, h of x is x plus 1 divided by x minus 2. Okay, now here we do have a rational function. We have a quotient of two polynomials. And because there is a denominator, we do have to worry about the denominator being equal to 0. We cannot have division by 0. There is no square root to worry about, but we cannot have division by 0. So the domain of the function h would be the set of all numbers that can be substituted into this function and have this function make sense. The only trouble spot would be x equal 2. If x is equal to 2, we would have division by 0. h of 2 is not defined. h of 2 would be 3 divided by 0, which is not defined. So the domain would be all x, such that x is not equal to 2. Or we could have written this in interval notation as minus infinity to 2, parentheses, union 2 to plus infinity, meaning all x values that are less than 2 or greater than 2, but not equal to 2. Okay, let's continue over here. Let's take the function big F of x is equal to the square root of x minus 4. Now for the domain of this function big F, we'd want the set of all x values for which we do not have the square root of a negative number. We do not have any fraction here, but we do have a square root. We can't take the square root of a negative number. So the set of all x values for which x minus 4 is greater than or equal to 0. We do not want the square root of a negative number, so what's under the radical, x minus 4, has to be either 0 or positive. Solving this simple inequality, set of all x values for which x is greater than or equal to 4. And we can write this in interval notation as bracket 4, comma, parenthesis, comma, plus infinity with parentheses, meaning x greater than or equal. The bracket means equal is possible, so greater than or equal to 4. Let's try now the function g of x, the square root of 5 minus x over x squared minus 4. To get the domain of this function, we're going to have to worry about both problems. We have a fraction, so we're going to have to worry about the denominator being equal to 0, and we have a square root, so we're going to have to worry about throwing out the negative numbers. Can't take the square root of a negative number. So all x such that, let's see what we have to do. Well, to begin with, we don't want the square root of a negative number, so 5 minus x has to be greater than or equal to 0. 5 has to be greater than or equal to x, or equivalently. X has to be less than or equal to 5. For example, you can substitute x equals to 4 into this. You get the square root of 5 minus 4 over 4 squared minus 4. That's perfectly okay. But if you try to substitute, for example, 6, you get the square root of 5 minus 6, the square root of a negative number. So x has to be less than or equal to 5. However, we do have a denominator here. We do not want the denominator to be equal to 0. To figure out what we have to throw out, let's actually set the denominator equal to 0. X squared equals 4, taking square roots of both sides. X is plus or minus the square root of 4, or plus or minus 2. So you would have trouble if x were equal to either plus 2 or minus 2. You'd have division by 0. The domain of the function big G, the set of all x values for which x has to be less than or equal to 5, or else you will have the square root of a negative number, but x cannot be equal to plus or minus 2, because you would have division by 0. If you want to write this in interval notation, it would help to look at this on the number line. Let's see, we have, let's say this is 0, 1, 2, 3, 4, 5, minus 1, minus 2, and so on. Now, let me draw the line right above the number line so that we'll be able to see it. All x values less than or equal to 5. So, starting here at 5, less than or equal to 5, except x cannot be equal to 2, so we have a whole of 2 or minus 2. So x cannot be equal to 2 or minus 2. All x values less than or equal to 5, but not minus 2 and not 2. This helps us to write the intervals that we need for the interval notation. We can write this as, well, from minus infinity to minus 2, union from minus 2 to plus 2, of course excluding the endpoints because we don't want minus 2 and plus 2 in, union from 2 to 5, but there will be a bracket on 5 because 5 is included. So we write it as the union, all x values less than minus 2, or between minus 2 and 2, or between 2 and 5, not including the 2 because of the parentheses, but including the 5, which we indicated with the brackets. Okay, it's a little confusing, but sometimes they write the answer in the back of the book in this notation. It would be helpful if you'd be able to translate this into this. And as I mentioned, the number line is very often helpful in doing that. Now let's continue with the following functions. F of x equals the square root of x minus 1, and g of x equals the square root of 7 minus x. Let's start by getting the domain of the function f and the domain of the function g. Now the domain of the function f would be the set of all x for which x minus 1 is greater than or equal to 0. We don't have any fraction to worry about, but we do have a square root. We cannot take the square root of a negative number, so we want to make sure that whatever's under the radical is greater than or equal to 0. And it's an easy enough inequality to solve. X minus 1 greater than or equal to 0 gives us x has to be greater than or equal to 1. You could write the domain in that form, or in the interval notation, 1 comma plus infinity with a bracket on the 1 to indicate that 1 is included, greater than or equal to 1. Okay, the domain of g over here, the set of all x such that 7 minus x is greater than or equal to 0. Set of all x such that 7 is greater than or equal to x. If 7 minus x is greater than or equal to 0, 7 is greater than or equal to x, or equivalently, x is less than or equal to 7. So the set of all x such that x is less than or equal to 7. And that also can be written in interval notation as minus infinity comma 7 with a bracket on the 7 to indicate all x less than or equal to 7. So we have the domain of f, set of all x such that x is greater than or equal to 1, and the domain of g, set of all x such that x is less than or equal to 7. Now when you have two functions like this, it is possible to define other functions from these two functions. We can define f plus g of x to mean f of x plus g of x. If we want to indicate the sum of two functions, we could have used another letter like h of x to indicate f of x plus g of x. But instead we're using this symbol, f plus g, to indicate the sum function. And this function simply means f of x, the square root of x minus 1, plus g of x, which is the square root of 7 minus x. Similarly, we could define f minus g of x to be f of x minus g of x, or the square root of x minus 1 minus the square root of 7 minus x. And let's say f times g of x to mean f of x times g of x, or the square root of x minus 1 times the square root of 7 minus x. Now these three new functions, which we are forming from the original functions, okay, we're interested in their domains. We know the domain of the function f and the domain of the function g. And the question is, what is the domains of each of these functions? Now, if we look over here, we're trying to figure out what values we could substitute in, which the function would make sense. We see that if we were to use, for example, x equals 8, the first part of this function would make sense. The square root of 8 minus 1 is okay, but the second part would not. The square root of 7 minus 8 would be the square root of a negative number. Similarly, if we were to substitute, for example, x equal to 0 in, the second part of the function would be okay. The square root of 7 minus 0 would be something we could deal with, but the square root of 0 minus 1 would be the square root of a negative number. So we're interested in the domains of these functions, and the one thing that occurs to us is that the first function has to make sense and the second function has to make sense in order for the sum, the difference, and the product to make sense. And because of that, these three have the same domain. The domain of f plus g equals the domain of f minus g is equal to the domain of f times g, and it's simply the intersection of the two domains. The domain of f intersect the domain of g, whereas the f function has to make sense and the g function has to make sense. So the domain of the sum, the difference, and the product, okay, they'll all be the same. It'll be the intersection of the two domains. In other words, I want the set of all x for which x is greater than or equal to 1, and at the same time, x has to be less than or equal to 7. That's the intersection of the two domains. The domain of f, of course, was all x greater than or equal to 1. The domain of g, all x less than or equal to 7. So the intersection of the two domains, the set of all x, which x is greater than or equal to 1, and x is less than or equal to 7. Okay? Which means that x is between 1 and 7, including the endpoints. In fact, we can indicate that. We could either write it all x such that 1 is less than or equal to x is less than or equal to 7, or on an interval notation, 1 comma 7 with brackets. X is greater than or equal to 1 and less than or equal to 7, meaning it's between 1 and 7, including the endpoints, 1 comma 7 in brackets. So the sum, the difference, and the product all have the same domain. Now, we can form two other functions from these. We can form the quotient f over g of x, define that to mean f of x divided by g of x, and g over f of x, and define that to mean g of x divided by f of x. So in our particular example here, we have f of x, which was the square root of x minus 1, over g of x, which is the square root of 7 minus x for f over g. And for g over f, the reverse, we have the square root of 7 minus x. We have the reciprocal of that over the square root of x minus 1. Okay, now when forming the quotient functions, we have to still make sure that f of x and g of x each make sense individually. So x has to be between 1 and 7. We have the same domain that we started with for the product and the difference and the sum, the intersection of the two domains. Except now we've introduced denominators where we didn't have denominators before. So we have, in addition to our other problems of worrying about square roots of negative numbers, we now have to worry about division by 0. So the domain of f over g, you take the same domain that you used for the first three functions, the sum, the difference, and the product, the intersection of the two domains, the set of all x such that x is between 1 and 7, including the endpoints. But then now you have to say, look, we have a fraction here. We didn't have a fraction before. We're going to have trouble if x is equal to 7, because we'd have division by 0. So we have to throw out x equal to 7. All x between 1 and 7, okay, including the endpoints, except now we throw out 7. So that gives us an answer of 1, 7, 1 in brackets, 7 in parentheses, meaning all x between 1 and 7 where we include the endpoint 1, where we exclude the endpoint 7. Okay, and the reason we did that is because this g of x function is now in the denominator, and x cannot be equal to 7. Now, let's look at the domain of g over f. The set of all x, like before, the f function and the g function have to each make sense if g over f is going to exist. So we start with the same basic domain, all x between 1 and 7. Except now, we have to throw out x equal to 1, because that would give us division by 0. So here it's all x between 1 and 7, except we have to throw out x equal to 1, because that would give us division by 0. And that would give us the interval from 1 to 7, parentheses on the 1, bracket on the 7, to mean, this means, of course, all x between 1 and 7, where we exclude the 1, but we include the 7. Okay, returning to our functions, f of x and g of x. I've just cleaned up the board a little bit. We know the domain of f, all x greater than or equal to 1, domain of g, all x less than or equal to 7. I want to introduce two other functions that we can form from these. We have f circle g of x, which is defined to be f of g of x, and g circle f of x, which is defined to be g of f of x. So you can think of this circle as an abbreviation for of, f of g of x, g of f of x. Okay, and what we're going to do when we're forming f of g of x is we're actually going to substitute g of x into the f function. In other words, f of, now what is g of x? G of x is the square root of 7 minus x. And here, replace f of x by what it's equal to. F of x is the square root of x minus 1. So f of g of x means f of this radical. G of f of x means g of this radical over here. Now, in order to finish this out, we have to understand what the function f is doing. The function f has one job. You give it a number, it subtracts 1 and takes the square root. For example, f of 7 is the square root of 7 minus 1. F of 8 is the square root of 8 minus 1. F of anything is the square root of that something minus 1. So if we want f of this radical, it's going to be the square root of this radical minus 1. F of 5 is the square root of 5 minus 1. F of 7, the square root of 7 minus 1. F of this radical, the square root of this radical minus 1. Now let's look, we want g of this. You give it a number, it subtracts it from 7 and takes the square root. So g of 2 would be the square root of 7 minus 2. G of 5 would be the square root of 7 minus 5. G of anything would be the square root of 7 minus that something. So g of anything is the square root of 7 minus that something. So g of this should be the square root of 7 minus this. F of g of x means we substitute g of x, the innermost function, into the f function. G of f of x, we substitute f of x, which is the innermost function, into g. All right, now, if we want to figure out the domain of either of these functions, let's say we want to figure out the domain of g circle f. In order for there to be the function g circle f, f has to be substituted into the function g. So f of x must exist. So we'll have to start with the domain of f. The domain of f would be the set of x for which x is greater than or equal to 1. Okay, let's work with now G circle f of x. We want the domain of this function. To begin with, in order to plug f into G, to substitute f of x into G, there has to be an f of x. So for G circle f of x, we start with f's domain. F's domain was all x, set of all x, such x is greater than or equal to 1. So that's what we start with. Now, in addition, the function that we finish up with has to make sense. So in addition, not only does x have to be greater than or equal to 1, which means that this radical is taken care of, but we have another radical here. 7 minus the square root of x minus 1 has to be greater than or equal to 0. 7 minus the square root of x minus 1 also has to be greater than or equal to 0. So the domain of G circle f is composed of two parts. To begin with, the f function has to exist because we have to substitute it into G. There has to be an f function, which means x has to be greater than or equal to 1. Then we look at the final result and say, okay, x is greater than or equal to 1. That takes care of this square root. But now we have this square root here, and we know that what's under this square root here has to be greater than or equal to 0. So 7 minus the square root of x minus 1 has to be greater than or equal to 0. Now let's see if we can work on simplifying this. We want 7 minus the square root of x minus 1 to be greater than or equal to 0. Okay, just like when we're solving a radical equation, let's isolate the radical. 7 has to be greater than or equal to the square root of x minus 1. And we'll square both sides. 49 has to be greater than or equal to x minus 1. Adding 1 to both sides, 50 has to be greater than or equal to x, or equivalently, x has to be less than or equal to 50. So the second condition, that 7 minus the square root of x minus 1 be greater than or equal to 0, is equivalent to x having to be less than or equal to 50. So for the domain here, we could write all x such that x is greater than or equal to 1, and x is less than or equal to 50, which means x is between 1 and 50. And we can write that 1, 50 in brackets to mean all x between 1 and 50, including the endpoints. All x between 1 and 50, including the endpoints. Let's go back. Let me write it over here for you. Let's look at the function and see if it makes sense. We claim the domain of G circle f is all x between 1 and 50, including the endpoints. Okay, let's see. If x is greater than or equal to 1, we won't have to worry about this radical here, because we will not take the square root of a negative number. If x is 50, 50 minus 1 will be 49. The square root of 49 is 7. If you let x be more than 50, this will be the square root of something larger than 49. This will come out larger than 7. 7 minus something larger than 7 will be a negative number. You can't take the square root of a negative number. So therefore, we have to restrict the x values between 1 and 50, including the endpoints. Okay, let's try another example. This time, f of x will be equal to 1 over x minus 3, and g of x will be equal to the square root of x minus 2. And we're going to form various functions from these two functions. Let's start with the domain of f. The domain of f, we don't have a square root here, but we do have a fraction. We would have trouble if we have division by 0. So the domain of x, all x except x cannot be equal to 3. And the domain of g here, we don't have a fraction, but we do have a square root. We know x minus 2 has to be greater than or equal to 0, or x has to be greater than or equal to 2. Okay, we don't want to have division by 0, so x cannot be equal to 3. We don't want to have a square root of a negative number, so x minus 2 has to be greater than or equal to 0, or x has to be greater than or equal to 2. Now, let us form f plus g of x, f over g of x, g over f of x. And well, that's it. We'll do the rest on the next board. Let me move this down a little. F over g of x and g over f of x. The sum function, we take f of x and we add g of x to it. I didn't write down this time the difference in the product, but f minus g of x would be 1 over x minus 3 minus the square root of x minus 2, and f times g of x, 1 over x minus 3 times the square root of x minus 2. And we know that the domain of the sum, the difference, and the product are all the same. The domain, for example, of the sum function, all x such that, now, each of these functions has to make sense. So x has got to be greater than or equal to 2, but x cannot be equal to 3. And we can simply write that. All x greater than or equal to 2, but not equal to 3. The intersection of the two domains. This function has to make sense, and this one. This will make sense so long as x is greater than or equal to 2. We have to remember that x cannot be equal to 3. Here we have no problem if x is equal to 3, but here we do. Here we would have no problem, for example, if x were equal to 1, but here we would. So x has to be greater than or equal to 2, but not equal to 3. Now, f over g of x means f of x over g of x. The domain of f over g would be the set of, we start with this as our basic building block. All x greater than or equal to 2 and not equal to 3. And we ask ourselves if we have to throw anything else out, because we now have a fraction where we did not have a fraction before. And we say, yes, there'd be a problem if x were equal to 2, because now that would give us division by 0. So we take the domain of f plus g as it was written, but now we throw out x equal to 2. So all x greater than or equal to 2, but not equal to 3 and not equal to 2. And this can be simplified. All x strictly greater than 2 and not equal to 3. Not equal to 2, so we took off the equal sign there. All x strictly greater than 2, but not equal to 3. Now, g over f of x is g of x over f of x, which is 1 over x minus 3. This was f of x over g of x. This is g of x over f of x. The domain of g over f, we start with the same domain that we had over here for f plus g. All x greater than or equal to 2 and not equal to 3. And we ask ourselves, does anything else have to be thrown out because we have a denominator? And the answer is no, because we don't have to worry about this function in the denominator being equal to 0, because a fraction is 0 when its numerator is 0. And that numerator cannot be equal to 0. So there's nothing that's going to make this denominator equal to 0. So we'll just end it with the same domain as f plus g. Now, I did not simplify f over g and g over f. What would happen if I did? Well, 1 over x minus 3 divided by the square root of x minus 2. You can think of this as the square root of x minus 2 over 1. So you can invert and multiply and get 1 over x minus 3 times 1 over the square root of x minus 2, or 1 over x minus 3 times the square root of x minus 2. Okay, instead of dividing by the square root of x minus 2, or the square root of x minus 2 over 1, we invert and multiply by 1 over the square root of x minus 2, giving us 1 over x minus 3 times the square root of x minus 2. Similarly, on g over f of x, if we were to invert and multiply, instead of dividing by 1 over x minus 3, we'd invert and multiply by x minus 3 over 1, and this would give us x minus 3 times the square root of x minus 2. Now, you might say, well, okay, there's no problem here. X is greater than 2, but not equal to 3. So I don't have to worry about x equal to 2 or x equal to 3, and we have x greater than 2 for the square root. But you might say, I can understand the x greater than or equal to 2 here on g over f, but why do you say x can't be equal to 3? I don't have any fraction, no division by 0. That's after it's simplified. You always have to remember where it came from. G over f of x, g of x over f of x only makes sense if there is a g function and there is an f function. If x were equal to 3, the f function wouldn't make sense. You wouldn't have a g over f, because the f function wouldn't exist. You'd never get a chance to invert and multiply. So even though it appears now that there is no denominator, you do not put back in the x equal to 3, because it came from a fraction. X could not be equal to 3. If x was not equal to 3, we did not have division by 0 here. This made sense, and then we could invert and multiply. But you do not put the x equal to 3 back into the domain. It stays the way it was. So the domain of f plus g, f minus g, and f times g is the intersection of the two domains. You use that as a basic building block for f over g and g over f. But then you ask yourself if, in forming a fraction, if I have to throw anything else out because of a worry of division by 0. And in this case, I had to throw out x equal to 2, but here there was nothing else to throw out. But just because you're not throwing out, you also don't put things back in. Okay. Now, I would like to finish off by doing, for this example, f circle g of x and getting its domain. If you remember, f circle g of x is f of g of x, which is f of. Now, g of x is the square root of x minus 2. We replace the innermost function by what it's equal to. We want now f of this. Now let's go back over here and look to see what the f function does. F of x is 1 over x minus 3. F of 5 would be 1 over 5 minus 3. F of 7 is 1 over 7 minus 3. F of anything is 1 over that something minus 3. That's all the f function does. Okay, you give it a number, it takes away 3 and takes the reciprocal. F of 7, 1 over 7 minus 3. So, if we remember that, f of the square root of x minus 2 would be 1 over the square root of x minus 2 minus 3. F of anything is 1 over that something minus 3. So f of this radical is 1 over the radical minus 3. F of the radical is 1 over the radical minus 3. So that would be f circle g of x, f of g of x. Now we want the domain of f circle g. In the previous problem, we worked on the domain of g circle f. In the domain of g circle f, we were plugging f into g, and f had to exist. Here it's the reverse. We are plugging g of x into f. In order for there to be an f of g of x, there has to be a g of x that we will substitute into f. So we start with the domain of g, which was all x greater than or equal to 2. And then we look at the final result and see if there's anything else that we have to throw out. Okay, since there has to be a g, in order to plug it into f, we start with g's domain, and that was, the domain of g was all x greater than or equal to 2. But now we look at the final result, and we ask ourselves, is there anything else that we have to throw out? Okay, well, we don't want to have division by 0, so the square root of x minus 2 minus 3 cannot be equal to 0. Okay, so we started with G's domain. X has to be greater than or equal to 2. And in addition, we cannot have division by 0. The square root of x minus 2 minus 3 cannot be equal to 0. Now, if we want to figure out what we have to throw out, let's take the other approach. Let's ask ourselves, when is the denominator equal to 0? How do you solve a radical equation? You isolate the radical. You square both sides in this case. And you see x equal to 11 would cause us problem, because we would have 11 minus 2 would be 9. The square root of 9 would be 3. 3 minus 3 would be 0. We'd have division by 0. So we will write the domain of F circle G as all x, such that x is greater than or equal to 2, but x is not equal to 11. All x greater than or equal to 2, but not equal to 11. There is no problem with x equal to 3. Okay, if x is equal to 3, 3 minus 2 is 1. 1 minus 3 is minus 2. You have 1 over minus 2. That's okay. So forget about F's domain. When you're working with f of g of x, it's g's domain that you start with. And then you look at the final result and see if there's anything else that you have to throw out. In this case, we see we had to throw out x equal to 11. So all x greater than or equal to 2, but not equal to 11. And that brings us to the end of this tape.